Math 5830, Analytics and Predictive Modeling. Course goals, structure of the course. Analytics and predictive modeling. We have some goals in this course. We want to explore how predictive models transform uncertainty in big data into knowledge. And these are two types of information. And we will actually introduce a field of mathematics called information theory in this course, because information we don't know is uncertainty. Information we do know is knowledge. And what we're really trying to do is translate our uncertainty into knowledge. We want to develop algorithms that are used in the data sciences for predictive modeling. And we want to introduce the skills necessary for working with large, complex data. The structure of the course: there will be 12 modules. There'll be about 3 to 5 videos. Each video is about 15 minutes. You'll attend course meetings for additional information, examples, discussion, review, questions, and so on and so forth. And this interactivity is actually very important. We build this course strictly from what is learned in a calculus sequence, calculus 1, 2, and 3. And my experience is that doing so, while very successful, does require a lot of interaction. So we'll be interacting quite a bit this semester. There'll be associated Jupyter notebooks that you'll need to work through. And there'll also be optional readings and exercises as necessary. And these are review as needed. So there's a lot of information on the website. You don't need it all. And much of what's on the website is there in case you want more than you got from the other 3 parts. There's additional support materials on the course site in addition to what's in the modules. Assessment in the course. The current plan is 10 weekly assignments. So we'll be doing roughly a module per week. And there'll be online quizzes and Jupyter notebooks. Some of these weekly assignments will be very short. Some will be more time consuming. Some will be conceptual. Some will be require the use of code, especially later on. The plan of 10 weekly assignments is that you have to get 80% or higher on all of them to pass the course. So if you do one and you get less than 80%, then you have to do it again. You have to eventually have 80% or higher on all of them. Now, once they're due, if you haven't achieved more than 80% by the due date, then the highest you can get is 80%. But this makes sure that everybody gets all of the content in the course, because it'll all be very important. You'll have a week to complete the midterm exam, and the last week of class we'll actually review, and you'll actually have the final exam as you work on it, and we'll actually be talking about the final exam as you actually are working on the final exam. Now, the final exam will have a project-like format, and it's not an individual project itself, although some of you may want to expand it into a standalone project. It will be project-oriented, however, to facilitate its suitability for a resume or its discussion in a job interview. In other words, the final exam is something you could use if you were in a job interview and say, I did this, I did that, I did this. In this course, I ended up doing this application. Now, the reason is this course has been carefully designed so you can have no background except a calculus sequence, and yet by the end of the course, you're ready to go to work. Ready, maybe even start your own company, do research in the field, whatever you want to do. you will be a member of the data science machine learning community at the end of this course. So I can say that because this is my 10th time teaching the course, and in all the previous 9 iterations, every student who wanted to go forward in this field did so. Some of them got jobs, some of them went to graduate school, but all of them moved forward in this field who wanted to. Now, there were some that took the course that went to, say, a graduate program in pure or applied math, and this was a good experience for them. But most of the students who took it for the reason of becoming a part or at least oriented into this field, and now are doing so, both private, both in academia and and employed. Move directly from this class into a job. So the structure of the course will have essentially 2 major parts. The first is complexity and information. We'll look at what is big data and then how to model complexity, nearest neighbor methods, metrics, information, decision trees, and ensemble methods. And after the first 7 modules, we'll have the midterm. The second part is algorithms as models. Now we'll learn about algorithms as models in part 1, but part 2 is where we're really going to put this to use. And we'll start with logistic regression and talk about kernel methods and neural networks, deep learning, and end up with multilinear algebra. Now, based on how the course goes, I may change some of the concepts of multilinear algebra. I'll have a better idea of what we as a class would want in that final module, but this is the plan as of right now. The other 11 modules, I can say, pretty much set in stone what they cover. And then, of course, we have a final exam due by the end of the semester. Background and expectations. We assume completion of a calculus sequence. Assume you've at least seen matrix algebra. Assume you have a willingness to develop the coding skills that you will need. Everything else will develop in the course itself. And when you get done, you will become a member of the data sciences community. So being a data scientist, what does it actually mean? Well, you have to be able to use abstract mathematics both conceptually and concretely. So you have to tell a machine what to do with a very large set of data. You can't think of that data concretely. It's too big. You have to think of this very concrete and very tangible set of data. You still have to think about it abstractly because it's so large and complex. We're going to have to assess the quality and utility of what the machine does. So these are going to be abstractly driven methods for assessing what a machine learning algorithm does. We're going to have to be able to use computers as a tool for working with data and as a context for developing and implementing algorithms. But that's really it. I'm not going to make you into a code warrior. Our coding is just so we can use code for working with data and implementing algorithms. So the calculus background required, again, this is all from a standard calculus sequence. Limits and derivatives will be used frequently, both conceptually and concretely. Logarithms and exponentials are very important. So important, in fact, that we'll definitely spend at least the first day, maybe the first 2 days, maybe the entire week, just talking about logarithms and exponentials. For example, in this course, we often work with functions like this: f of p is equal to p log p plus 1 minus p log 1 minus p. Derivatives which we'll call gradients in the course. That's the standard name for a derivative, is a gradient. And they're also very, very important. And so we're going to start, when we meet on Monday, reviewing the required math, making sure that the calculus background that we need is firmly established and recalled before we start moving into anything else.